like it. I think you're gonna feel you belong. A nocturnal vacation, unnecessary sedation. You wanna feel at home 'cause you belong. Welcome to my nightmare.
Welcome to my breakdown. I hope I didn't scare you. That's just the way we are when we come down. We sweat and laugh and scream here, 'cause life is just a dream here. You know inside you feel right at home here. Welcome to my breakdown. Whoa. You're welcome to my nightmare, yeah.
Well, welcome. My name is 𝗬𝗦𝗕𝗦𝗧. I will be your presenter today. Thank you for attending. Originally had it just explaining transfer functions, Laplace transforms, and then at the end I kind of added welcome to my nightmare. So I hope you enjoyed a bit of Alice Cooper. A little bit of guidelines. Your microphones are off. You will be able to ask questions through the Q&A box, and I will read the questions, and I will also and answer your questions that way through the chat or Q&A box. Either one works. I will answer them at the end. Now, there is a 10-second time delay between the moment I speak and the moment you hear me and see me. And so if you think that light travels at 300,000 kilometers a second, I'm actually 3 million kilometers away from the Earth. And I got that because I actually managed to get hold of some element 115 from Bob Lazar. You can look him up on the internet and put it in my flying saucer. And now I'm actually broadcasting from outer space. Your questions are anonymous, and so therefore you can only I can see your questions. So there's no bad questions. I encourage you to ask a lot of questions. And if a question is not answered to your liking or there's not enough time, you could always feel free to reach out to me through the following contact information. Yes, all my contact information is actually in little black and white squares, apparently. So this is a series. This is the 14th webinar that I've put together. You can see here I've had all the previous 13. They are recorded. If you do wish to view them, just let me know. I can send you the link, and you can watch them. Probably even be able to fast forward through all some of the boring stuff that I'm doing right now. As I said, this one is being recorded as well, and so we will be able to email you the link up to the videos after to the webinar after it's done. Safety moment, carbon monoxide. Reason why I talk about this right now is probably more about the charcoal grill. We have to be careful, especially in summertime, to be able to charcoal indoors. Not a good idea. And carbon monoxide is an odorless, colorless gas, and can be quite deadly if not taken care of. I know I have 2 carbon monoxide detectors in my house. I probably should have one in the basement as well. And so just be very, very careful about that. Like I said, especially nowadays with charcoal and even probably just gas grills as well. A little bit about Lakeside. It does say 325 employees there. It's actually, we're close. We're over 400 employees. We have offices, obviously, in Mississauga. We have our newer facility. It's not new anymore, but newer facility in Dundas, Ontario, where a lot of the valve repairs and fabrication is done. skids manufacturing and so forth done in Dundas, Ontario, which is north of Hamilton. We have offices Sudbury, Port Elgin, Thunder Bay, and Winnipeg. And Lakeside is part of the Emerson Impact Partner. There are 21 partners. I was self-employed many years ago, and I actually did a lot of contract work for many of these Emerson Impact Partners. And why go with the Impact Partner Network as opposed to having a monolithic Emerson presence? They want to have more of a local presence, be able to service our customers better. And so we actually are the point of contact between you and Emerson to be able to find you the proper solution. And I always say any feedback is good feedback. So always encourage to give us any feedback, whether it's this webinar or any other experience, interactions you have with Lakeside. There is a link typically on emails to be able to fill out. And like I said, any feedback is good feedback. A little bit about myself. I've been doing this actually since 30 years, which is kind of more like 34 years now. I do control loop tuning services, control audit services, troubleshooting services. We also do DCS alarm metrics. Any of you in operations right now, probably look at your DCS alarm page. It's probably full of alarms, and probably a lot of them are probably not relevant. So what we do is that we actually go through, take over like 30 days worth of alarms, analyze them, and make recommendations on how to make the alarms relevant. We found that 80 to 90% of your alarms come from 8 sources or less. And I do teach courses as well. I do teach a process control techniques 1 and 2, loop tuning 1 and 2. I do teach also a basic instrumentation course. If you're interested, you can consult our website under events and training, I believe, and you'll see I do have courses scheduled for in the fall. And I do have a couple of gentlemen here that help me out. There's a third one actually that's not shown here. Andrew gives me a good hand, and Dean as well, as does another gentleman called 𝗪𝗘𝗦𝗧𝗔𝗬. And there we go. There's our courses that I offer right there. And if you're really, really bored, you can go to our website and look up. We have blogs. I have blogs as well. They're humorous kind of stories, but they have a technical aspect, and there's a bit of a moral to the story. So feel free to go ahead and read those blogs. What are we going to cover? Who was Mr. Laplace? I know the Laplace Transform, and some of you encountered that and says, I really don't understand how this works. We're going to cover the basics of this. I'm not going to go into detail, and I'm probably be quite convinced that some of you probably know a little more about Laplace Transforms than I do. We'll say, who was Mr. Laplace? What is a Laplace Transform, and why use it? Why was this invented? Why are we still applying it? And the properties of Laplace Transforms. And then we'll talk about how is this related to PID control. We're going to actually derive, in a simplistic way, we're going to derive the lambda tuning rules. Those of you who've taken my loop tuning course probably know that I teach lambda tuning, and it has its roots obviously in Laplace Transforms. And then at the end, we'll talk about where is Laplace after that? Where is it? So Mr. Laplace, Pierre-Simon Marquis de Laplace, was a mathematician, obviously, but he did quite a bit of work, quite the accomplished mathematician. He did some work on tides, astronomy, electromagnetism, and probability. I'll find that on Wikipedia, but he's obviously a very accomplished mathematician. Now, what is a Laplace transform? This is the actual transform there. How did he come up with this? I really don't know. I mean, it must take quite a bit of cerebral power to be able to conceive of this. And so f of s, which are the actual, in the s domain, is the integral of f of t in the time domain times e to the minus st dt. Why? Why do we do this? Because the physics and the world is described in differential equations. And differential equations are not always the easiest to solve. So the idea is that you can use what's called a Laplace transform table. You can put in your differential equation, transform into a Laplace domain. That then turns it into like an algebraic mathematical equation. You could do your work in the Laplace domain and then bring it back into the time domain. And so it's a mechanism to simplify the solving of differential equations. And some of you may remember that the first derivative, dy dt, is just a simple multiplication by the Laplace operator s times y of s. So if you want to take the first derivative of a function, you just multiply by s, do the inverse Laplace, and there you go. And the integral is obviously 1 over s. That is the integral. Let's talk about different processes here. First order process, probably one of the more common, the most common type of process that we model, let's say a flow. We will model a liquid pressure. We will model it as a first order process. And here's the actual differential equation of a first order process, where y of t will be your flow, u of t will be the output change to the valve, which would cause the flow to react. Now, if we look at it from so this is what an actual first order process looks like. One time constant, tau. And you can see here, I know I mentioned here process dead time. I'm going to deal with that elephant in the room later on. So I'm not going to deal with it right now. And this is the actual Laplace transform for a first order process, Kp over tau s plus 1. Kp being your process gain, your process sensitivity, how much of a change I get in my process for a given change in my output, which is the input to the process. And so therefore describes the amount of change I get here for a given change on my output. How do you model? You can model that here. I'm just showing you basically it's a filter block. So this would be the blue line here. If I go back, that's the blue line there. And the process measurement out here would be the yellow line. Second order systems. So these are systems that have not one, but 2 time constant. So there's a differential equation for a second order system. Now, second order systems can come in various forms, depending on the value here of zeta. That is zeta there. And if zeta is greater than or equal to 1, a second order system looks like this, where you got your output change. And you can see here before the first order kind of took off directly, here it's actually taking longer to take off. There's more inertia. There's a second time constant. This is what the second order differential equation in Laplace domain looks like. And as I said, zeta is greater than or equal to 1. If zeta is less than 1, means it's actually an oscillatory type of response. Now, I mean, I can explain this a little bit more, and maybe my next webinar will be on root locus and actually be able to explain this a little bit more in detail using root locus, but I decided to keep it simple for now, just to keep it simple. And here is how you model a second order system. You put 2 first orders in series. And so you can see here, so the output here will see a lagged response coming from the previous block. And so here's my step change. I get a first order lag here, and I'll get my second order lag that side. Integrator. So integrating processes are processes that are marginally stable. They don't settle out. Tank levels are integrating processes. If I put more stuff into my tank that I'm taking out, I'm integrating the difference between all the flows in minus all the flows out. This is a differential equation here for an integrator. And in Laplace domain, it's just Kp over S. Kp being, your process gain. And so here you can see the blue line is the output command to the valve and your process. In this example here, I'm putting slightly less into my tank than I'm taking out. dropping it, I'm putting much less into my tank, my process drops. And when I do the next bump, I'm putting more into my tank than I'm taking out. My process keeps on creeping upward. Note that gas pressures are also integrating processes. If you remember your universal gas law, PV is equal to nRT. So that's what grade 10 chemistry, best 3 years of my life. The pressure, if we PV, so we say that V, the volume is constant, is equal to N, the number of molecules, R, a constant, and let's say T, the temperature is constant. Your pressure is directly dependent upon N, the number of molecules. If I'm putting more steam molecules inside my steam header that I'm consuming, I'm accumulating steam molecules, my pressure will ramp up. Conversely, if I'm putting less steam molecules in my steam header than I'm consuming, then my pressure will ramp down. Here's a couple of different ways. I mean, here we have an integrating block. This is all done in delta V. Another easy one is actually having a recursive addition block. So it will actually then integrate using an add block. Let's talk about our good old friend, Mr. PID, proportional integral derivative. And here is the actual equation of the PID. So E of t is the error, Kc is the gain, Tr is the integral time, could be seconds per repeat, could be minutes per repeat, and Td is T uppercase D is derivative time. Now here I'm doing derivative off the error. So here is a Laplace equivalent. So Kc is on the outside, your controller gain. TRTD s squared, it's a second order, plus TRS plus 1 all over TRS. TR again being the integral time. That is known as the standard form. So a lot of times if I go do some tuning on a system that I'm not 100% familiar, I need to find out, usually I can find this equation or perhaps this equation in documentation, and it'll tell me if it's a standard form, could be a classical or series form, could also be a parallel or non-interacting form. Now, about 90 to 92% of the control loops use PI only. In a previous life, previously I actually developed a Lakeside tuning index where I would look at over 5,000 PID tuning parameters, PID blocks, and I found that, and I was surprised actually, that up to 8 to 10% actually loops use derivative, and a lot higher than I thought. So just as a sidebar. Now for PI only, we set TD to 0. This is a transfer function, Kc bracket TRS plus 1 all over TRS. And G sub C, incidentally, the transfer function, is a transfer function of a controller. And there's a step response here. I did this where I changed the set point. You can see here, the blue line is command signal going out of the PID block. I make a set point change here. My PV is yellow. It is constant. As soon as I make a set point change, my error, I develop an error. I get my proportional kick, after which the integral takes over and keeps ramping up, ramping up, ramping up. Here, I've obviously disconnected my process from the feedback loop. Now, let's talk about the elephant in the room, dead time. And dead time or time delay, don't call it lag. Lag is something else. Call it dead time. Essentially, it's the time it takes for when I make a change before I observe it. That is time delay or dead time. And the Laplace transform is e to the minus STD. T little d being the time delay. But you can see here, this is not a nice clean algebraic kind of polynomial that we have here. And so it makes the handling, when you do some solving for it, it makes it kind of a little bit messy. And so a lot of time you could use something called the 𝗦𝗦𝗕𝗦𝗧 approximation, where you would actually use this expression here. You can go probably second or maybe third order, so up to here. It will develop a reasonably good approximation of dead time, and you can incorporate that in your transfer function. So I'm not going to deal with it. It really can begin to complicate the math very, very quickly. So I'm just going to sort of, at this point, conveniently ignore it for now. Again, what I will be talking, maybe my next webinar will be on root locus, where we can visualize it a little bit better and see the effects of the dead time. But if the dead time is negligible, then we can safely ignore it. And I'm just going to conclude here. I know this is a bit fairly quickly, and hopefully I didn't go too fast. But as I mentioned before, I teach loop tuning courses, and one of the loop tuning rules that I teach is called the lambda tuning rule. It's also known as a pole zero cancellation method. So to develop the lambda tuning rule, we got to remember here, we got our GC, which is our controller, our PI controller. I'm not going to do PID. And GP is your process transfer function. Now, to actually calculate and develop the closed loop transfer function, the way you do it is that you go through once across GCGP divided by 1 plus one time around. 1 plus GCGP. So that's sort of to develop so now we're going to develop the transfer function between your set point and your PV. So let's go back to here. Let's say our GC is going to be our PI, KC, controller gain, bracket TRS plus 1, bracket all over TRS. That is our transfer function for our controller. And GP of S is going to be a first order. Again, we're going to safely ignore the dead time for now, for simplicity reason. So therefore, G of S, the closed loop transfer function, as we just showed, is GCGP, controller times the processor function, 1 divided by 1 time around. So far, so good. So therefore, GCGP, again, I don't want to go to the laborious math here, is divided by GCGP is KCTRS here. Now, if one of the rules for lambda tuning rule is that you make the time constant of the process equal to the integral, or the integral equal to the time constant, I should say. What we're trying to do there, we're trying to cancel out the dynamics of the process itself. And so substituting tau for TR, those two terms get canceled out. That's what we're trying to do. We're canceling out the process. And therefore, GCGP is equal to controller gain, KC, KP, all over TRS. Still with me? Okay. So the closed loop transfer function is as such. I'm not going to repeat it here. And so the denominator, this part here, I'll put that over the common denominator. And so you can see the top denominator and the bottom denominator cancel out. So that then is equal to KCKP over TRS plus KCKP. So what we're trying to do here, we're developing a first order closed loop transfer function. So if I divide the top and bottom by KCKP, this is what I get. And this is the end goal here. This is what I'm looking for, a closed loop response following a set point change. That is the closed loop transfer function. That is what I'm looking for. So therefore, if I will need to back calculate how do I achieve that, I will make my controller gain equal to 1 over Kp times Tr over lambda. And that here is a lambda tuning rule for the gain and for the integral action. So you can see here with Laplace transform, I know we talked, and I kind of joked at the beginning, welcome to my nightmare. We talked a lot about, how, and a lot of people in university says, I know I learned all that, but I really couldn't apply it to the real life. I hope here this kind of giving you a bit of a hint as to there is an application, and I'm trying to slowly build a bridge between theory and practice, and hopefully this webinar has been able to kind of build a little bit of that bridge. So where is Laplace? I've actually been there. I've driven by it. It is a little town just outside of New Orleans right there. So I'm going to open it up to questions, and hopefully I've explained things pretty well. And hopefully, like I said, you can feel free to ask me questions. If I'm trying to remember, how do I? Audience. It's been a while since I've actually been able to view the questions. Just bear with me. There we go. All right. My apologies for all this. So one question is, how do you determine if the PID is in standard form versus interactive? Very good question. By looking at the transfer function, the actual transfer function of a series or interactive is slightly different than a standard or ideal form. I know there's no standard terminology. So there's the PID algorithm that I showed you is either known as standard or ideal. There's another one called, it's either an interactive or classical form, is a different form. And what it does, it's actually based on the transfer function, the series form or interactive form is a little bit more restricted theory-wise, but it actually doesn't make much of a difference for most applications. So does deadband add to response time? Not exactly understand the question. And deadband or dead time, maybe perhaps if it's dead time to the response time, yes. There's no getting around, even in your closed loop response, that your response will include the dead time as well. I hope that I answered that question properly. Where is the PV filter time constant come into the equation? Very, very good question. So I always discourage the use of dampening altogether. Reason being because as you do your first order bump test, you want to see your true process, as I showed you the first order response. Putting more and more filtering, and filtering is there to attenuate, note my language, attenuate high frequency noise. But the more and more dampening or filtering applied to your signal will become more and more dominant and add another first order constant there. And essentially, you can actually turn your true first order process into a second order process because you put too much filtering on your PV. So therefore, like I said, I would discourage, if you are going to use some PV filtering, I would encourage you to put it in the DCS, not in the transmitter. That way we can all see it. Excellent. I've got more questions here. What's the difference between lambda tuning and Ziegler-Nichols tuning? What type of processes should lambda tuning be used? All right, very good question. So the main difference between lambda tuning and Ziegler-Nichols is that lambda tuning gives you a first order overdamped response. That means there's no overshoot, undershoot, overshoot, undershoot, which makes it then not oscillatory. It is, whereas Ziegler-Nichols, you make a set point change, it will surpass the set point, come back down, undershoot, overshoot. That is known as an oscillatory response. Reason why I don't like that method is because it has a natural resonant frequency, such as some of you might Google it, Tacoma-Narrows Bridge, where it actually had a natural resonant frequency and it fell apart. What that does is that you got to understand from a frequency perspective, a PID controller is bombarded by all sorts of variability from very, very slow frequencies to very high, fast frequencies. And tuning a controller using Ziegler-Nichols, an oscillatory response, actually has a natural resonant, will actually amplify, by virtue of the tuning itself, will amplify part of that frequency response. On top of that, we should always be asking ourselves, how do I want my controller to respond? Is it practical? Do I want my boiler feed water to be oscillating? It's probably not a good idea. And so therefore, like I said, to make a long story even longer, I discourage the use of Ziegler-Nichols tuning. What would the effect of derivative be on the system response? That is, I knew there would be someone asking me about derivative. I was trying to get out of it. The response would be different. It's probably, I'd have to probably think about it a little bit more to be able to actually respond. Typically, derivative is used. You could see here the lambda tuning rule. I use the one parameter, the integral parameter, to cancel out the one time constant that we modeled. If we model our process like a temperature control, if we model it with two time constant, a second order system, then we can use the derivative to cancel out the other time constant. And that's where derivative will come into play. So another question. In your experience, how to differentiate between temperature loops that are self-regulating versus integrating? Is there a way to simplify if prior to do a bump test? So I mean, probably what I think the person is referring to is that if I do a bump test on my temperature and I do my response, and maybe here I can draw it out here, and it's probably going to be very, very poor drawing. Let me see if I can go back right there. So I do my bump test as such, and my not like that. Very, 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 very slow type of response from my temperature. What you could do, because now what we can do is model this temperature as what we call a near integrating. We're cutting a corner, we're making an approximation, and if we don't abuse it, we'll be okay. What do I mean by that? A near integrating process. So I could do a bump test like this, do another bump test like this, do another bump test like this. I don't know why it keeps doing that little blip there. And my process then can probably respond like this, and slowly respond like this, and respond like that, and respond like this. I don't know why those blips keep appearing. And so if we were to do our bump test here, this would have kept on responding like this, but instead we make a series of step changes, and we can approximate a time constant, a very, very long time constant or time constants. We can approximate them as integrating processes and to them as such. Another question. Hi, not directly related, but is the industry ready to accept MPC? From your experience, is MPC better than PID? So those of you who don't know, MPC is model predictive control. And so the answer is depending on the application. MPC can be used to control multiple processes. They are very sophisticated controllers. From a very simple basis, if your process has excessive amount, a lot of process dead time delay. As we know, a PID algorithm is a very impatient beast. What it does, as soon as I make a change, it expects to see a response right away on a process. And that doesn't happen. Well, I'm going to add more to the output, add more to the output, add more to the output. And eventually what's going to happen is going to overcorrect and end up oscillating. A model predictive control takes into account the dead time by modeling the process itself. So is it better than PID? In probably some applications, yes, especially if your process has excessive amount of dead time or time delay. And a lot of application is probably the same. There's no real advantage to using MPC versus PID. Awesome. So we shall see here. Just waiting if there's any more questions. All right. And you still have time to ask me a question. There we go. So the other question is, there are other variations of PID, like PID gamma, that deals with wind-up lambda tuning, works for it too? And the answer is yes. Yeah, so some of the PIDs, depending on the vendor, some of them want to avoid, when you make a set point change, to avoid the set point kick, that initial kick that I showed you initially. Some of them can do that, bypass that first scan to be able to avoid that kick for whatever reason. But yes, it does work for that as well. Another question here. Can you provide examples of processes that may require derivative action? Now, people always love derivative. I think I explained that before, where the process would be a temperature control, and what derivative does is a process that has a lot of inertia. So you imagine temperature control through a heat exchanger. There's a heat transfer that has to happen before we actually see a change in temperature, be it heating or cooling. And so what we do is that derivative allows us to kickstart the process, give it a good kick to overcome that inertia. And eventually, as the temperature is approaching set point, derivative is there to put on the brakes to be able to make sure that we don't overshoot our set point. You could see we actually use derivative control in every day. You think about driving, you know, you got your foot at this accelerator at this angle to go at 70 kilometers an hour. You come off the red light, you just put your foot at that angle. You know, eventually you'll get there, but what we do is that we actually press it down further to accelerate, and as we approach 70 kilometers an hour, then we kick back. There's another example of using derivative control. You guys are great, asking great questions. So can I always cancel denominator with a numerator? Doesn't it make sense? The system unstable, I'm actually canceling 1 0 with one pole in the system. And the answer, that is the basis of this method here, is yes, it's called a pole zero cancellation. And that's what we're trying to do. Does it make the system unstable? I'm not 100% sure. I mentioned at the beginning, I know there's some people out there that are probably smarter than I am, and obviously this person is smarter than I am regarding this. But not to my experience, obviously, because I've been doing this for a long time. But I'd be willing to talk about it more directly offline should you wish to contact me. All right, I'm still waiting for more questions here. I'm not going away. I just kind of play a bit of music here.
Welcome to my nightmare. I think you're gonna like it. I think you're gonna feel you belong.
All right. Any other? I'm just going to wait another minute or two, and then certainly want to thank you very much for attending. Enjoy this nice weather here. Oh, I got another question here. So when do you use IPD, PID, or different forms of the PID? So the person is asking, sometimes you could do PI on air, D on PV. You can do PID on air. You can do I on PV, PD on air. You can. When do you use different types of? Again, it depends on your application. I sort of going to sound like a lawyer. It depends, but it depends on your application. It depends on most of the time. The one thing I want to underline, if you are going to use derivative for most, not all, but most applications should be done on the PV. Reason being is that derivative moves the output proportional to the rate of change of the error. And so what happens if I make a set point change, my error went from being very, very small to very large in a very short period of time. Derivative, if done on the error, would react to that fast change. Whereas if your set point is constant and your PV deviates from your set point, you do develop an error. There's no difference between the rate of change of the error and the rate of change of the PV. So for most applications, PID should be done on PV and not error.
Welcome to my breakdown.
All right, gonna wait another bit of time here, and then we will call it a day. You guys have been great. Thank you very much for attending. Great questions, and you are more than welcome to reach out to me. And possibly look out for another webinar explaining root locus, how do transfer functions relate to root locus, stability, oscillatory behavior, and so forth. And there, maybe we could delve more into how does dead time come into play. Awesome. Thank you very much. Have a great day.